So we first consider stochastic multi-arm-bandit setting, where there are k arms, so k possible actions. For all actions A, there is a stochastic process XAT with unknown distribution rho A. Okay, so there is hidden distribution for each arm, and the hidden distribution generate IID rewards for each action. The bandit game is at each round T, an agent or a learner choose an arm AT among K possible actions or among K possible arms, and they'll receive a reward XATT. So here AT is the index we choose. XATT that follow V. So they follow VAT. Okay. So simply, I will use XT is to denote XATT for the remaining slide for the ease of notation. And in this case, so as I told you just before, we can observe the reward only for the played arm AT. Okay, so there is hidden distribution for each arm, and we have to learn the hidden distribution from the received reward, but the rewards only revealed to the learner for the selected arm. Okay, so the goal is build a sequence of strategy A1 through AT-1 using the observed reward that comes from the played arm. And we want to maximize the expected return from time t1 to time capital T. That is our final goal. Applications are many. There are many applications. Every possible task that the underlying properties should be extracted from adaptive observations, and the trajectory is also very important. Okay. So casino case, clinical task, or recommendation task, all the tasks have to use multi-arm bandit concept to design very nice sequential decisions. Okay. So among many stochastic bandit setting, I will introduce Bernoulli bandit and all the algorithms for the Bernoulli bandit. So Bernoulli bandit, I think the most simplest form of multi-arm bandit setting, where XAT, the reward distribution, the reward process is IID following the Bernoulli distribution with parameter mu A. Okay, so every time when you play action A, the return is independent to the previous observations and independent to the future. Just give us some coin tossing with property mu A. So the bandit game is the learner chooses an arm AT at time t and receive the reward xt, and the xt follow a Bernoulli distribution with parameter mu AT. So the reward is either 0 or 1. And the goal for this Bernoulli bandit is we want to maximize the reward, expected reward, from time t1 to capital T. In other words, we want to minimize the regret. So here, what is regret? So regret is the regret compared to the policy that playing the best arm all the time. The best arm, of course, is the arm having the largest expected return, the largest mu A value. So where mu star is max over whole actions, max of mu K. Okay. So for the Bernoulli stochastic bandit setting, there are many theories because of the simplicity. Essentially, most of them analyze the asymptotic algorithm, asymptotic regret analysis. What is the regret order as the end time capital T go to infinity? What is the regret growing speed with respect to the capital T is interesting question, research question. So the Lai and Robbins first present very nice row bound result. The row bound means any algorithm cannot beat the regret row bound. So we cannot design. It is impossible to design a decision-making process for the Bernoulli bandit setting, which having less regret compared to this regret row bound. What is this regret row bound? So Ryan Robbins' result is this: a uniformly efficient algorithm such that the regret is a small o order of capital T to the alpha for all mu. Then for all case, we satisfy this lim inf capital T equal to infinity. The expected number of plays of arm A over log T is greater than or equal to 1 over divergence between mu A and mu star. Here the divergence is scale divergence between two Bernoulli distribution with parameter mu A and parameter mu star. And for the Bernoulli distribution, the scale divergence simply like this. Okay. So what is the meaning of this result? Is essentially for any arm, the number of plays of each arm should be at least 1 over KL divergence times log T. We have to visit every single action at least this amount. If the arm is very close to the best arm, we have to play more. Intuitively, we can explain this fundamental low bound like this. When two arms having very similar hidden parameter mu value, then to discriminate which one is better, we have to play many times to achieve a very accurate estimation on the hidden parameter. We have to play many times to learn the hidden parameter mu A very accurately. That's why 1 over KL divergence here, constant here, okay, and log T is very important. Let's go back to the concentration inequality. For instance, for Hastings inequality, we have this, the probability of let's say 1 over n summation of xi I1 to n greater than or equal to expectation of x plus some epsilon. This is less than or equal to exponential minus n times something, and something comes from the distribution of xi, the upper bound and lower bound of each random variable, and epsilon. There's some epsilon square in the numerator, and denominator is just a sum of upper bound and lower bound difference square. Okay, so when we can set this value equal to 1, and when we have n is equal to log t, exponential minus log t is just 1 over capital T. When we have this concentration bound, we can do this for the exception case. So, okay, so let's imagine we played on random, we play on action log t time, and let's assume this constant is just 1. Okay, and then we can say that with probability 1 minus 1 over capital T, our estimated empirical average or our empirical estimation on the hidden parameter having error bound plus minus epsilon with probability 1 minus 1 over t. If this plus minus epsilon is enough to discriminate to the other arms, to discriminate which one is better compared to which one is better. So let's assume all the arms having expected rewards difference at least 2 epsilon times. Epsilon difference is enough. So with probability 1 minus 1 over capital T, we can find the best sum accurately. No mistake. But with probability 1 over capital T, we have mistake. But even if you have mistake on choosing which one is the best from the empirical average, still the number of place is just at most capital T. So the expected regret is 1 over capital T times the number of place. That is just constant. Okay, so that is the magic of log T, and we will learn this one again and again. Okay, so don't worry, even if you cannot understand why log T here at this moment, I will explain again. Anyway, so why this is a regret? So when we are row bounding the number of place of each arm, from this we can directly make regret row bound. Okay, so because what is the regret? Regret is simply this. This is equal to summation small k equal to 1 to capital K mu star minus mu k times nk capital T. So the regret is the reverse difference times number of place of each arm. That is basically the expected regret. So when you up row bounding the number of place, from this we can row bound the regret, and the regret is proportional to. So from this the regret is row bounded by this small k1 to capital K mu star minus mu k over k divergence mu k and mu star times log T. So for the Bernoulli stochastic bandit case, every algorithm has at least this amount of regret. Okay. So how to show such row bound? The row bound proof is interesting, I think. So with the laws of generality, assume that all the arms sorted by the expected reward. So mu1 is the largest one, and then mu2, mu3, and so on up to mu_k. And consider a perturbed model. So this is not original model. We change a little bit on the hidden parameter. So consider a perturbed model and change mu2 to the mu2 prime, which means so that mu2 prime is strictly or slightly bigger than mu1, and keep the remaining thing to the same. So we only change the mu2 to the mu2 prime, and everything the same. Then the expected reward order becomes mu2 prime, mu1, mu3, and so on up to mu capital K. So let's say this model is the first P1 model, and this one is P2 model, and all the rewards comes from P1 distribution when we follow the original model. All the rewards comes from P2 distribution when we follow the second model. Okay, so why we have to design such a two model? One is original and one is some kind of perturbed model. So in reality, in real life, essentially we don't know the current reward process comes from which distribution model. We don't know the reward comes from P1 or P2. We don't know. And here in P1 and in P2, we have different best sum. In P1 model, we have the first arm as the best arm. But for the P2 model, the second model, the portal model, the second arm is the best. U2 prime is the best. Okay, so because of that, if we cannot discriminate P1 and P2 from observation, we have to pay something. We have some regret. Because we cannot discriminate P1 and P2, we cannot know which one is the best. First arm is the best, and second arm is the best. Okay, I want to say okay. Let's assume the world either comes from P1 or P2. But we don't know. We don't know current reward process, random process comes from P1 or P2. We have to find this from the observations. Okay, since P1 model and P2 model, they have different the best arm. If we cannot discriminate P1 and P2, we cannot choose the right one. We cannot choose the best one. Right? Then the question is, how many samples and what kind of decision process, what kind of policies can give us nice regret, can give us very tiny regret and give us the right information to discriminate P1 and P2. That is the main question. Okay, so let P1 and P2 denote the probability measure of the original model and the perturbed model. And then from this, I want this. On the P2 model, the number of plays for the second arm is less than 1 minus delta times log t over KL divergence mu2 and mu star is small o t to the alpha minus 1. We have this from the uniformly efficient algorithm assumption. Since regret have to have T alpha, small order O of T alpha for every possible model, for every feasible model, from the Markov inequality, we should have this from Markov inequality. Why? From the uniformly efficient algorithm assumption, we have regret for every possible model like this. Okay. Uniformly efficient algorithm has to satisfy this regret condition for all possible models. This is the second model, also feasible model, and from the uniformly efficient rule assumption, the expected value of t minus n to t should be O of small o of t to the alpha, because the second arm is the best on the P2 model, right? So the number of plays you play the suboptimal arms should be upper bounded by small o of capital T alpha. And this is the case. This is equal to P2 capital T minus n to t is bigger than capital T minus 1 minus delta log t over divergence. This is essentially negligible compared to capital T, and when you apply the Markov inequality, you have this. So we know that with very, very high probability, because alpha can go to 0, n to t should be should be greater than 1 minus delta log t over divergence between mu2 and mu star. We have this result. Okay, so let's define LT is equal to s to t log mu2 over mu2 prime plus n to t minus s to t log 1 minus mu2 over 1 minus mu2 prime, where s to t is the number of positive outcomes by playing 2. So this is the number of success and this is number of fails, or this is number of positive outcomes and number of zero outcomes when you play the second arm. We have this result. The probability n to t is less than or equal to 1 minus delta log t over d mu2 mu star is this is less than t to the minus 1 plus alpha from the previous slide. And this is just I rewrite this probability. So take the integral to the event area using the P2 measure. That is upper bounded by this. Why? Here we add one more condition. This L value is less than 1 minus 2 alpha times log t. And when you add some more condition, then the probability becomes shrunk, right? So we can easily see when you add more condition, then the probability decrease. This inequality comes from that fact. And since we assume that L is less than 1 minus 2 alpha log t for this event, and the definition of LT is essentially, this definition of LT is probability 1 over probability 2 of this observed event. Why? The only difference between probability measure 1 and probability measure 2 is mu2 and mu2 prime. We only change that parameter. And the event having mu2 probability for the positive event under P1 model, we have mu2 prime probability for the positive outcome under P2 probability measure. We have fraction like this. Oh, sorry, this is log. For the zero outcomes, the original model having 1 minus mu2 probability, but for the same event, the P2 measure having 1 minus mu2 prime probability measure. When you take log P1 event over P2 event, we have LT value. So LT function value basically just give us the information about P1 over P2. So using that fact, we can add t to the 2 alpha minus 1 since we assume L is upper bounded by this. And we have this inequality sign. And we change dp2 to dp1. So basically, from here to here, we multiply this dp1 over dp2. That is LT for the event. And we assume LT is upper bounded 1 minus 2 alpha log t. That's it. So therefore, we have the probability under first model, n to t is less than or equal to this, and L is less than or equal to this, is upper bounded by d to the minus alpha. And this also almost 0 when capital T go to infinity. So now let's conclude the proof. So let's assume n to t is strictly greater than 1 minus delta log t over the KL divergence mu2 and mu star. And I will show this is true under the condition, the previous property close to 0, this one. Okay, right. So since this property go to 0 as t go to infinity, when this is true, this does not hold, right? Because the event inside property is n to t should be less than or equal to 1 minus delta log t over d, and L is less than 1 minus 2 alpha log t. When this is true, then it holds. And in the previous, we assume that, we find that the probability go to 0 as t go to infinity. Okay? So I believe this is true. So I will show this more formally. So assume that this is not true. So I will prove this by contradiction. So assume that this is not true. Then we can make delta, I think delta equal to 2 alpha. Expectation L given n to t is equal to n to t times KL divergence, less than or equal to 1 minus delta, this one. Under the assumption n to t is less than 1 minus delta log t over the mu2 mu star. So we have this. And when we set delta equal to 2 alpha, this value is upper bounded by 1 minus 2 alpha log t, because we set mu2 prime slightly bigger than mu star, mu1, that is mu1. So d2 mu2 mu star is less than d mu2 mu2 prime. So this value is bounded by 1. This value bounded 1 minus 2 delta. So we have this, which make n2t less than 1 minus delta log t over d mu2 mu star, and L less than or equal to 1 minus 2 delta 2 alpha log t is true. Okay? So if this is not true, this is true. But since in the previous slide we showed that this property go to 0 as t go to infinity, this contradicts to the previous slide. Okay? Okay. I think it is better to set 4 delta here. Anyway, 4 alpha. Anyway, so when you assume this is not true, then we can show that this is this property close to 1, but this contradicts to the previous slide result, which make by mathematical by contradiction statement, we have that n to t is greater than or equal to 1 minus delta log t d mu2 mu star. Okay, so which means we complete the proof when we assume a uniformly efficient algorithm that has this regret bound. Then essentially the number of observations for each arm divided by log t, always lower bounded by 1 over KL divergence between mu a and mu star. That's it.